Hello everyone, my name is Dr. Jon Seol, a faculty of Department of Computer Science at MGA. Today I will be presenting my research on modeling quantum jumping dynamics with random initial state probabilities using Markov chains. Okay, quantum systems, especially quantum jump phenomena, are critical for advancing quantum technologies like computing and communications. So this study explores the world of quantum jumping and focusing on how we can model these dynamics when we start with random initial state. We will be using Markov chain as a key tool in our research. Okay. Right. Introduction. Before we dive into the detail of on our study, let's take a quick look at the structure of the presentation. This outline will give you a roadmap of the key sections we will be covering. Okay, introduction. And second is Markov chain modeling approach. Number 3, simulation and analysis. Number 4, results and analysis. Number 5, implications and conclusion. Okay, quantum computing. The key concept of this research is 3 parts. Quantum is superposition, entanglement, and quantum interference. Okay, superposition is unlike classical bit, okay, which are either 0 or 1. However, quantum qubits can exist in a state of both 0 and 1 simultaneously. Okay, this is a superposition. Superposition enables quantum computers to perform multiple calculations at once. Okay. Next, entanglement, where 2 qubits become linked and the state of 1 instantly influences the state of the other, regardless of distance. Okay, so it makes the more complex computation and faster processing. Okay, and third one is quantum interference, which is quantum interference. Okay, quantum interference is a phenomenon used to manipulate qubit during computations. So it helps amplify correct solution and cancel out incorrect one. Okay, so let's summary of these quantum key concepts, 3 of them, and then quantum jumping definition is quantum jumping is a fundamental phenomenon in quantum mechanics. Okay, where a quantum system transition between discrete energy state, typically accompanied by absorption or emission of energy. Okay, so this process is critical for understanding and controlling quantum system in quantum computing where qubits rely on a precise state transition for computation. Okay, so in this study, quantum jumping is modeled using Markov chains to simulate quantum dynamics, offering insight into how random initial state probabilities influence system behavior. These findings have significant implications for quantum technology, including sensing, communications, and the development of more refined quantum algorithms. Okay. All right. Let's see the classical versus quantum algorithm and their comparison. Classical algorithm is normally operate on binary data using zeros and ones and deterministic in nature, leading to predictable outcomes. It is suitable for most traditional computing tasks, right? But it is limited by exponential growth of data, which can affect the performance and scalability. So what about quantum algorithm? It utilizes qubits that can exist in multiple states simultaneously, as its superposition, so can solve certain problems much faster than the classical algorithm. Okay, and so that's why non-deterministic. Okay, non-deterministic. So and it's like a phenomenon like entanglement and superposition for parallel processing is available, and potential to revolutionize fields like cryptography and optimization and material science. Okay, so let's see the comparison. The quantum algorithm offers exponential speed of specific problems, but classical algorithms are currently more practical and widely used, but face some limitation as problem scale. So now hybrid approaches combining both may offer immediate benefit until quantum computing matured, because of the hardware system is not completed. Okay, let's move to next. Quantum jumping in machine learning. Recently, we have some research studies, particularly some indicates significant potential for using quantum jumping in optimization and pattern recognition and classification tasks within machine learning. Okay. From this finding, it suggests that the quantum properties could be effectively leveraged to enhance the capability of existing algorithm. Okay. Right. Traditional modeling. Previously, it approaches to incorporate quantum mechanics in machine learning, often rely on complex quantum mechanical formalism, and this method, even though this is very powerful, it can be challenging to implement and require deep understanding of quantum mechanism. Okay, so I propose approach to make quantum-inspired technology more accessible. I propose using Markov chain model with randomly initial state probability. So this approach allows for more straightforward simulation and analysis of quantum random dynamics, making it more accessible to researchers and practitioners, like real industry engineer without any background in quantum mechanics. So by focusing on the probability nature of Markov chain, we can simulate the non-linear transitions characteristics of quantum jump, offering a practical way to explore their application in machine learning. Okay. A methodology and proposed model. Objective of this methodology, the primary goal is to simulate quantum jump dynamics within machine learning systems. This simulation aims to leverage the unique properties of quantum jumps to enhance machine learning algorithm, especially in areas like optimization and pattern recognition. Okay, so key concept is in this model, the quantum state are represented as discrete element within a Markov chain. The transition probabilities between these states are designed to reflect probability nature of quantum jump, allow for accurate simulation of their dynamics. Okay, this approach offers a more accessible way to model quantum phenomena, making it easier to integrate these concepts into machine learning system. Okay. Simulation process, initialization and iterative simulation, analysis and conclusion. Okay, so begin by defining quantum state relevant to the system, such as energy level or spin configurations, assign random initial state probabilities to each quantum state to capture the inherent uncertainty characteristics of quantum systems, and set up transition probabilities between states that align with the dynamics of quantum jumping, that is ensuring that they reflect the probability nature of these transition. Okay. Iterative simulation. This simulation proceed through discrete time steps representing the evolution of system of time. At each time step, updates the state probabilities using Markov chain transition matrix, which governs the the transitioning from one state to another state. Okay. Okay. This iterative process continues, allowing the system to evolve according to the predefined quantum jumping dynamics. And analysis, after completing the simulation, generate a sequence plot that visualizes the evolution of state probabilities over time. These plots provide a clear view of how the system's quantum state change. Okay, so it conducts statistical analysis to evaluate the variability and convergence of the simulation result. Okay. In conclusion, this simulation process offers a comprehensive method for modeling quantum jumping in a controlled and iterative manner, providing valuable insight into how this dynamic can be applied to machine learning system. Model verification, comparison and evaluation. So first step in validation of the model involves comparing its behavior to more complex quantum mechanical method. These quantum mechanical methods serve as a benchmark for assessing the accuracy and realism of a simplified Markov chain approach in simulating quantum jump dynamics. Okay, by comparing outcomes, we can identify any fine tune the model to better align with established quantum mechanical theories. Okay, evaluate the model of overall effectiveness in representing quantum jump dynamics, focusing on the how well the simulator captures the stochastic nature and transition characteristic of quantum systems. In conclusion, through this comparison and evaluation, the model validation process ensures that the proposed method reliably represents quantum jumping, providing confidence in its application to machine learning system. Okay. Application in machine learning, optimization and data processing, and predictive model and security algorithm. Right? Let's see. Figure 1, model of the basic state transition of initial transition and observe. S1 is initial, S2 transition, S3 observe. Okay. Transition diagram shows state S1, S2, S3 with corresponding transition probability, right? So QP12, like that, quantum probability 1, 2, and 2, 1, like that. Okay, S1 is initial state, S2 transition state during quantum jump, S3 is observer state post quantum jump. Okay. Okay, simulation dynamics, Markov chain and iterative approach, simulation outcomes. So 3 steps. Okay, there is 4 different types of random number generation method. Quantum random numbers, quantum jump numbers, and general random numbers, and quantum-like numbers. Okay. Okay, statistical analysis and validation emphasized the analysis of variability and convergence properties across different methods, right? So it shows the comparison of simulation result with established quantum model, right? So it also shows the effectiveness of Markov chain model, right? Implications for machine learning. We can understand the transient behavior of quantum jump, and the implication of different random number generator can guide the design of more robust quantum-inspired machine learning algorithm. Okay. So we can share insight from the simulation that suggests potential area of optimization in this algorithm. And figures and visualization. Let's see. This is the result of this discussion. Figure 2 present a simulation of general random number generation method, and number 3 analysis of the probability. Initially, the state probability shows moderate variability, reflecting the deterministic randomness. We can I just use random number generator in Python code of the classical method. Over time, these probabilities gradually converge in a stable distribution, indicating the Markov chain reaches like a equilibrium. This convergence is less volatile compared to the quantum-based method, so emphasizing the predictable nature of classical random number generation. Okay, so in figure 3, standard deviation of state probability is shown, so representing the variabilities at each time step. Okay, initially the standard deviation is moderate and mirroring the controlled randomness of general random number generation. As the simulation progress, the standard deviation in decrease steadily, and indicating reduction in variability and the stabilization of the state probabilities. Okay. Okay. Number 4 present a simulation of quantum random number generation method. Number 5 is analysis of probability. Figure 4 present the simulation of quantum number generation method with state ranging from 0 to 9. And number 5 presents the analysis of simulation. Okay. Figure 4 is like a average probability of each state of at each time step. Initially, the mean state probability exhibit. It does just show show significant variability reflecting the inherent randomness of quantum random number generation. Okay, as the simulation process, this probability converges toward a stable distribution, indicating the system's progression toward equilibrium. Okay, so this convergence pattern highlights the effectiveness of Markov chain in stabilizing state, the probability of time, even with high initial randomness. Okay. In Figure 5, the standard deviation, the state probability is plot representing the variability in state probability in each time step. Okay. And number 6, the quantum jump number generation method. Figure number 7, analysis of the probability. Okay. Figure number 6 presents across all 5 sequences 1, 2, 3, 4, 5, and the simulation revealed the range of behaviors influenced by the random initial state probabilities and the transition metrics. The mean and standard deviation of state probabilities across these sequences provide a comprehensive view of the system's variability and convergence properties. And the differences observed in each sequence highlight the sensitivity of the Markov chain dynamics to initial conditions and transition probabilities. Okay, so emphasizing the importance of careful selection and calibration of these parameters in practical applications. Okay, figure number 7 demonstrates that the standard deviation, which represent variability and decrease over time. Initially, the variability is high due to the random start, but as the system approaches equilibrium, this variability diminish. Okay. All right. Let's see the figures 8, quantum-like number generation method, and number 9, figure number 9, analysis of the probability. Okay, figure 8 shows the simulation quantum-like number generation method with state ranging from 0 to 9. Quantum-like numbers aim to mimic the probability behavior of a quantum system using classical method. In our simulation, we simulate quantum-like numbers by generating number binary strings and converting them to decimals. Quantum-like numbers displays the properties such as uncertainty and randomness, similar to quantum random number. However, they lack the true randomness inherent in quantum phenomena and deterministic given the same input. Okay, the quantum-like number may find application when true randomness is not critical, such as simulation and modeling. Okay. Okay, key findings: 3-part: quantum randomness, general random number, quantum like numbers. Okay, quantum random numbers and quantum jump number display true randomness, but we just highlight the unpredictable state transition associated with this method. In general random numbers, this number leads to deterministic randomness and thus like a very smoothly state transition compared to quantum method. Okay, and quantum like numbers, it is these numbers strike a balance between random number and computational efficiency, like efficient, right? There is some limitation, like a note. It is noted that they do not fully replicate quantum behavior, right? Okay, future research directions, like advanced quantum RNG technique, like enhancement, like a focus on enhancing the authenticity of quantum simulation as hardware evolves. Okay, and refining quantum-like algorithm and hybrid approach, exploring like a combination of classical and quantum techniques. This is very practical and now focusing on the hybrid model. And quantum-inspired algorithm and machine learning advancement. We need to discuss the potential of quantum-inspired algorithm to revolutionize various industry, right? And machine learning advancement, we can explore how the advancement in machine learning can enable solution to complex problems, right? And limitation. We have some limitation like a simplified model, like simulation may look over real-world complexities, right? So leading to less accurate representation. And model also has some limitation. We need to discuss the limitation of using simplified model in capturing the full scope of quantum dynamics, right? And computational demand. It's like a true quantum randomness, right? Because of the method may not fully capture the true quantum randomness due to computational constraints, like that, and statistical analysis need refinement and detailed analysis required. And applicability, variable findings, and context specific. We have many things in on the context. Actually, that means we just focus on importance of considering the context in which the finding are applied, right? and evolving technologies. We need to discuss the need to stay updated with technological progress to ensure the relevance of the findings. Okay? All right. Conclusion. In this research, I'd like to conclude by summarizing the random number generation method, emphasize their impact on Markov chain dynamics, and the importance of selecting appropriate method based on the specific needs of application. And practical consideration, we need to get the balance between the high randomness and unpredictability of quantum-based method and efficiency and determinism of classical method. So in future research, we have some disbalance as a critical consideration for future research and application development. Okay. All right. Thank you for watching video. Bye bye.